Alright, so now I'm going to show you how to approach question number 4, where we're given a square matrix of n by n, and this is n. So, and then we're given, for example, based on this rule, we're going to construct a 4 by 4 matrix. So each value in the column is 1, and then below that you have negative ones. Above that you have ones, and the rest of your values are 0. This is a matrix of this type. Now I'm going to call this matrix a D matrix. D4 matrix. And the rest of the values 0. This is a D4 matrix that follows these rules. So now the question is, how do we determine the determinant of D4, then the determinant of any n by n matrix? So let's try to get to work on that. So the way in which you can approach the determinant is cofactor method. And you can approach this cofactor method either by using rows or columns. And the cofactor method is basically you're multiplying the value of each thing, and then it's either positive or negative. It's an alternating cycle, and then you get the determinant of the matrix by removing that. So firstly, I'm going to start off by taking cofactor method of row 1. So the thing is, in a diagonal, if this is a diagonal of 1s, and that's a diagonal of 1s, and that's a diagonal of negative 1s, and the rest are all zeros for all we care about. In this cofactor expansion, since it's basically, say it's row 1, you basically get A11, and the determinant of the matrix without A11 then becomes minus A12, determinant of A12, so on and so forth. But since A1n is equal to 0 when n is greater than 2, there are only 2 terms in row 1 that anyone really cares about. So we are going to define this. I'm going to write this down as, so the determinant n is equal to, say we're going to take this, we define as D4. Say in Dn, we're going to take 1, 1, and then in the matrix of Dn, excluding row 1 and column 1, minus Dn row 1, column 2, and the matrix of Dn 1, 2. This is always equal to 1. That's always equal to 1. So we're basically getting that the determinant n is just Dn 1, 1 minus Dn 1, 2. The magnitude of the determinant by getting rid of this. So if we go back up here, if we got rid of this column and this column, what happens really is that we're getting back to these 3 cells right over here. And these 3 are actually D3, because this you're going from, if you're looking at this is D2. You add the same things, become D3. You add the same 4, you become D4 matrix. So this actually becomes the determinant of n is equal to the determinant of n minus 1. But this is when it gets more complicated. The determinant of n12, when we take out the second column, so let's take that for D4, and if we do that, what happens is we get, when we remove that, we get, so we take out row 1 and column 2, negative 1, 1, 0, 0, 1, 1, 0, negative 1, 1. Right? So we get negative 1 as the corner. But still remember that that's the only non-zero is the one above and the negative 1 below. So when the 1 above, we get this. But for this, getting cofactor is really simple. Because we just take negative 1, right? And we get negative with that value because it's the start 1. And then when we get rid of this and this, we end up with D2. This is D2 right here. So we get determinant of n minus 2. Minus det n minus 2. So the determinant of n, we have just proven, is sum of the determinants of the last two numbers. And since it's a recursive pattern, let's start off by getting determinant of 2. Because we need a base case, right? Determinant of 1 is always going to be 1. And determinant of 2, 1 times 1 is 1, plus is 2. So determinant 3, 2 plus 1 equal to 3. Determinant of 4, 3 plus 2 equal to 5. And you can follow this recursive pattern to get any determinant of n for a matrix of type D. So by the properties of the cofactor expansion, we're trying to see where we are multiplying by 0. We're trying to minimize that, and then by cutting it, we end up, if this is a matrix, we isolate this, and we isolate this, and we find that if this is Dn, we find that is Dn minus 1. And that is how you can approach this question.